Good morning, students. Till now, we have discussed about the basics of complex algebra, loop closure equation for slider crank mechanism, both inline and as well as offset slider mechanism, loop closure equation for 4-bar mechanism. Then we have derived the expression for velocity and acceleration of a slider crank mechanism using complex algebra. Then at the end I listed the formulas which are useful in solving the problems on slider crank mechanism. After that I solved problems. After that I solved all the problems that are being given in the textbook and as well as appeared in the previous question papers. As far as the problems are considered, whatever we have solved it, with respect to the problems on slider crank mechanism, the first and initial thing to be remembered is you have to draw the diagram of the slider crank mechanism along with the vector representation, inclinations, theta 2, theta 3, what is A, what is B, what is D, in order to identify as and when the problem is given on it, you must be able to understand and list out according to our notations what are all the given things in the problem, because of which I have separately listed out the formulas along with the figure after the derivation. So students, you please remember all the 5 formulas along with the diagram. Second is you have to take the anti-clockwise as positive and clockwise as negative. First is figure, second is formula, and the third one is sign conventions. These are the 3 things which are must. Whether the figure is going to be given or not, irrespective of it, you must draw it and you must list out what are the given things in our notations, like small a, small b, theta 2 is how much, what is alpha 2, how much is alpha 2, that and all. Then using the formula you can solve it. Now today I am going to solve the problems on offset slider crank mechanism. First of all, or before offset, in inline slider crank mechanism, the link 1, that is the point A, link 1 or the point A is a fixed link and the fourth link is a slider. So link 1 and link 4. Link 1 is the fixed link, that is point A, which you can see in the diagram, and link 4 is the slider. These 2 links are in line with each other. Then it is called inline slider crank mechanism or simply a slider crank mechanism. Suppose if the fixed link 1 and slider, that is link 4, link 1 and link 4 are away from each other vertically by some distance. Instead of, you can see in the figure 1, what is the figure 1? It is a slider crank mechanism, specifically inline slider crank mechanism, because the point A, which is a link 1, and a slider, that is link 4, both are in line with each other. So therefore here there is no confusion. It is inline slider crank mechanism or simply a slider crank mechanism. Suppose if instead of on the same line link 1 and link 4, if they are separated by a distance, vertically, then it is called as a offset slider crank mechanism. Vertically they are separated by a distance, where that separated distance is called eccentricity. So if the link 1, that is point A of the slider, point A of the mechanism, and the link 4, that is slider, both are being separated by a distance called eccentricity, then separated by a distance, or they are away from each other vertically, then it is called as a offset slider crank mechanism. Now you can see in figure 2, link 1 is the point A, which is a fixed link. Link 2 is the crank, that is AB. Link 3 is the connecting rod, that is BC. And instead of slider which is in line with the link 1, it is being at a height of small y or small y from the point D. So therefore here the slider, that is link 4, and the point A, which is the link 1, both are separated by a distance equal to y, where y is known as eccentricity. Now this is the case 1. In the case 1, it is a offset slider crank mechanism in which the angles are theta 1. The point A is in line with the reference line or horizontal line, therefore theta 1 is equal to 0. Then theta 2 is the angle made by the crank. Theta 3 is the angle made by the connecting rod. And now the theta 4 is the angle made by the slider, which is equal to 270 degrees. So in this case, or in this type of offset slider crank mechanism, theta 1 is equal to 0 and theta 4 is 270 degree. Theta 1 is the angle made by the fixed link 1, or the point 1 with reference to the horizontal line. Theta 1 is 0 because horizontal line and the link 1 both are coinciding. So theta 1 is 0, whereas the angle made by the slider, which is equal to 270 degrees. So this is one type of slider crank mechanism, offset slider crank mechanism. That is why I wrote it in the bracket case 1. In case 1, theta 1 is equal to 0, whereas theta 4 is equal to 270 degrees. Where what is y? Y is the eccentricity, or it is the distance from the slider to the link 1 or to the reference line. And in addition to the, in general, in a slider crank mechanism, as we discussed in case of simple mechanisms of module 1, we have identified how many links? 4 links. Fixed link, that is link 1, link 2, that is crank, link 3, that is connecting rod, and link 4 is a slider which moves on the horizontal surface. But because the slider is at a height of y from the reference line, therefore in addition to 4 there will be one more link, that is link AD, which you can see in the figure, where C, small c is the vector of the link AD. Small a is the vector of AB. Small b is the vector of the link BC. And now CD is is one more link where its vector form is small c. So c is the length of the link CD or the position vector of the point D with respect to D, and y is the eccentricity. But here you remember, so the length of the link CD or eccentricity, one or the other same. So C is equal to y, because how much distance it is away from the reference line, that is eccentricity y, it will be as good as it is equal to the length of the link CD. So therefore, now in this case 1, how to remember? Theta 1 is equal to 0. That is, angle made by the link 1 is 0 and angle made by the slider, that is link 4, is equal to 270 degrees. In this type of offset slider mechanism, how to find the velocity of the slider, angular velocity of the connecting rod, and similarly with respect to acceleration, how to find the acceleration of the slider and angular acceleration of the connecting rod. Whatever we have calculated in our earlier problems, velocity of slider or piston, acceleration of slider or piston, angular velocity of the connecting rod, angular acceleration of the connecting rod. So these are the 4 things mainly which we calculated in our earlier 4 to 5 problems on slider crank mechanism. Now, how to find the same, that is, how to find the velocity and acceleration in case of offset slider crank mechanism. Students, there is no, once again, a derivation is to be derived. Only here, compared to inline and offset, so only one formula is going to change. What is that one formula? That is the angle made by the connecting rod, that is theta 3. So theta 3 formula, which I wrote it here as theta 3 is equal to sine inverse of C minus A sine theta 2 by B, where theta 3, as I wrote very clearly, that it is the connecting rod angle to be calculated, and C is nothing but y, or it is nothing but eccentricity or the position vector of the link 4. So C is equal to offset distance minus A. A is the length of the crank or the crank radius, and theta 2 is the crank angle. So, and small b is the connecting rod length. So this is the only one formula which it is going to change if at all the problem is asked on offset slider crank mechanism. So only connecting rod angle formula is different. Remaining all formulas is same as the slider crank mechanism. So remember, you have to along with the 6 formulas which we know already in case of slider crank, you must remember one more, because connecting rod angle formula is different for offset. Remaining formulas are same. So what is theta 3? It is equal to sine inverse of C minus A sine theta 2 by B, where C is nothing but y, which is equal to eccentricity, and A is the crank radius, theta 2 is the crank angle, and B is the connecting rod length. Except this, remaining formulas are same. But this is one case of offset slider crank mechanism. So theta 1 is equal to 0, theta 4 is equal to 270. Similarly, now I can find the offset slider crank mechanism of one more type, that is case 2. If I look at this diagram, now theta 1, that is the angle made by the link 1 will be 270, whereas the angle made by the slider or the link 4 is coinciding with the reference line, therefore theta 4 is equal to 0. So theta 1 is 270 here and theta 4 is 0 degrees. Now in this type of offset slider crank mechanism also, the only connecting rod angle theta 3 is going to change. That is, theta 3 is equal to sine inverse of minus a sine theta 2 minus c by b, where a, it is crank radius or crank length, which will be given in the problem. Theta 2 is the crank angle, which will be also given, and c is nothing but what? It is the eccentricity, which is equal to y, small y, whole divided by b, which is the crank connecting rod length. So using this formula, theta 3, you can calculate whenever the offset slider crank mechanism in which angle of the link 1, that is theta 1, is equal to 270 and theta 4 is equal to, that is angle of link 4, that is slider, is equal to 0. So you have to remember all the three figures. First, inline slider crank mechanism, next offset slider crank mechanism of case 1 and case 2. And remember, case 1, theta 1 is equal to 0 and theta 4 is equal to 270. Whereas in the case 2, here now whatever you can see on the slide, so theta 1 is equal to 270 degrees, whereas theta 4 is equal to 0. So in offset slider crank mechanism, only connecting rod angle formula is different. Remaining all formulas are same. So how to find the crank angle in case of the first case and second case? Only to be remembered. So therefore, in addition to the first 6 formulas, what I gave in case of slider crank mechanism, you need to remember 2 more formulas, because theta 3 formula is different for a offset slider crank mechanism of case 1 and as well as case 2. If you are able to remember only theta 3, remaining formulas are same, so that you can successfully solve the problems which will be given even on offset slider crank mechanism. When theta 1 is 0, theta 4 is 270, theta 3 is one formula. Case 2, theta 1 is 270, theta 4 is 0. In that case, theta 3 is this. So like that, this is the summary of the formulas on all the 3 types of slider crank mechanism. Inline, first one, offset, in which theta 1 is 0, theta 4 is 270 degrees. Third is also offset, in which theta 1 is 270, theta 4 is 0. So you have to remember 3 figures and totally 8 formulas for slider crank mechanism, that is inline slider crank mechanism. In case of inline slider crank mechanism, you have to mug up the 6 formulas. In addition to that, if the problem is given on offset slider crank mechanism of either case 1 or case 2, you need to remember the 2 more formulas, so that is to find the connecting rod angle theta 3, which will be different in the case 1 and case 2. So totally you need to remember 8 problems, so that you can solve definitely without doubt any problem which will be given on slider crank mechanism definitely. Now let us go for the problems on offset slider crank mechanism. So this is the problem which is appeared in June 2014-15 and as well as December 2015. Now sometimes statement only given, or sometimes along with the statement figure is given. So whether it is going to be given or not, you need to remember whatever I told while listing the formulas, all the 3 figures. Now if you look at this problem, the offset slider crank mechanism is shown. The offset slider crank mechanism is shown in the figure. The crank OA is rotating uniformly at 15 radians per second counterclockwise, and length of crank OA is equal to 20 mm and connecting rod AB is equal to 90 mm. Find first one, velocity of the slider and angular velocity of the connecting rod. Second, acceleration of slider and the angular acceleration of connecting rod. So you need to find all the four things. But first of all, if I look at the diagram, 50 degree is theta 2, that is the angle made by the crank, and 10 mm, which you can see in the figure, is the eccentricity, that is y or small c, which is equal to 10 mm. Now if I look at the diagram, one can identify the given mechanism is a offset slider crank mechanism in which theta 1 is equal to 270 and theta 4 is equal to 0. So it is nothing but case 2. Whatever just now I told, the two cases of offset. Now if I read the sentence, so offset slider crank mechanism is shown in figure. So what kind of offset slider crank mechanism? Where the theta 1 is equal to 270 degrees. The angle made by the fixed link 1, that is point O, is 270, and angle made by the slider, that is theta 4, is equal to 0. This is the case 2 of our offset slider crank mechanism. Next, what is saying, the crank OA is rotating uniformly at 15 radians per second counterclockwise, means anti-clockwise. So therefore, I can write, if I look at the units of 15 radians per second, means directly this is the angular velocity of the crank, that is omega 2, which is equal to 15 radians per second. In the bracket we write down anti-clockwise, because crank is rotating in anti-clockwise direction. How? In the statement C, counterclockwise, or it is also called as anti-clockwise. Next, length of crank OA. So according to our sign notations, it is small a, which is equal to 20 mm, which in turn, that is 0.02 meters. You have to divide with 1000. 20 by 1000 is 0.02. Next, connecting rod AB is equal to 90 mm. So according to our notation, small b it is, which is equal to 90 mm. 90 by 1000 is 0.09 meters. Now from the figure, I can write C, small c, or small y, that is eccentricity, is equal to 10 mm. That is 10 by 1000 again, 0.01 meters. Then also from the figure, 50 degree, as I told just now, theta 2, that is 50 degree. By default it is here measured anti-clockwise. So theta 2 is 50. And it is rotating uniformly. Crank is rotating uniformly. Therefore, for a uniform speed, the angular acceleration of crank, that is alpha 2, is equal to 0. So these are the things. Now find acceleration of slider, that is Vc, and angular velocity of the connecting rod, that is omega 3, is equal to what? Similarly, second bit, acceleration of slider, that is AC, is equal to what? And angular acceleration of connecting rod means alpha 3. I should find Vc and omega 3, two velocities and two accelerations. Linear acceleration of slider AC and angular acceleration of connecting rod alpha 3. So now first find out, take down all the formulas. First I have to calculate, right, theta 3, that is connecting rod angle, theta 3. So this is the case 2 of offset slider crank mechanism, where theta 3 formula, from it if I just note down here, it is sine inverse of minus a sine theta 2 minus c by b. So sine inverse of minus a value is 0.02 into sine theta 2 is sine 50 minus c, or that is nothing but offset distance 0.01 divided by b, small b value is 0.0. Now if I simplify, then I am going to get 16.34 degrees, which is minus. Now once again theta 3 is equal to 360 minus 16.34. Whatever you are going to get should be deducted or subtracted from 360 degrees. Then the connecting rod angle will be 343.66 degrees. This is the only one which is different. Next, go for the velocities. First, angular velocity of the connecting rod, that is omega 3. So omega 3 from the formula list, whether it is offset or inline, except theta 3, remaining all formulas are same, whatever I told. So therefore omega 3 is equal to minus a omega 2 cos theta 2 by b cos theta 3. Here a is known, which is 0.02, omega 2 it is given as 15 radians per second, 15 it is, and cos theta 2 is cos 50 whole divided by b is 0.09 into cos of theta 3, just now we calculated, it is 343.66. If I simplify, I am going to get omega 3 value as minus 2.233 radians per second. So therefore omega is equal to, I will write only figure, that is 2.233 radians per second in the bracket. Because of negative, I will write it as clockwise. Like that I can calculate the angular velocity of the connecting rod. So once you get the angular velocity, calculate the velocity of slider, that is linear velocity of the slider VC. Once again note down the formula, it is a omega 2 into sine of theta 3 minus theta 2 whole divided by cos theta 3. Here everything is known. A is 0.02, omega 2 is 15 radians per second, sine of theta 3 343.66 minus theta 250 whole divided by cos theta 3. If I substitute and simplify, I am going to get minus 0.286 is the value, because it is a velocity, means linear velocity. So units are velocity meters per second. Angular means then only it goes radians. Next, therefore, velocity of slider VC is equal to, only I am going to write the figures, numerals 0.286 meters per second in the bracket. Because it is negative, I will write it, the slider is moving towards the crank end. If it is positive, the slider will move away from the crank end. So like that I have completed the velocities. Next, go for the acceleration. First, angular acceleration of connecting rod, that is alpha 3. Once again from the formula you write it, what is alpha 3 is equal to what, and in the alpha 3 formula you can remember, here there is a term which contains in the numerator alpha 2. Here alpha 2 is equal to 0, therefore total minus a cos theta 2 alpha 2 becomes 0. Thereby alpha 3 is equal to a omega 2 square into sin theta 2 plus b omega 3 square into sin theta 3 whole divided by b cos theta 3. So if I substitute all the values and simplify, I am going to get alpha 3 value directly, a positive value, that is 41.376, that is alpha 3, and it is acceleration, not acceleration, angular acceleration. If it is acceleration means meter per second square. When you say angular acceleration, instead of meter, radians will come. So therefore alpha 3 is 41.376 radians per second. Because it is positive, in the bracket I will write down anti-clockwise. Next, after finding angular acceleration of connecting rod, go for the linear acceleration of slider, or simply acceleration of slider, that is AC. Once again note down the formula. Once again look at in the formula which you wrote. Here the first term in the numerator contains alpha 2. As here alpha 2 is equal to 0, therefore total this term gets vanishes or becomes 0. Thereby AC is equal to minus a omega 2 square into cos of theta 3 minus theta 2 minus b omega 3 square whole divided by cos theta 3. Here all values are known. Substitute and simplify. I am going to get acceleration is equal to minus 1.4142 because it is simply acceleration, means by default linear acceleration, unit will be meters per second square. So like that you can solve the problem on offset. Now I have solved one example on offset slider crank mechanism in which theta 1 is equal to 270 degrees and theta 4 is equal to 0. Similarly, let us take the second problem. The offset slider crank mechanism is shown in figure. So by the crank OA is rotating uniformly at 10 radians per second counterclockwise, and length of crank OA is equal to 15 mm and connecting rod AB is equal to 80 mm. So find velocity of slider and angular velocity of the connecting rod. Second, acceleration of slider and angular acceleration of connecting rod. Now, if I look at first of all, what is the first line? The offset slider crank mechanism is shown in figure. So, if I look at the diagram which is given, I can say that theta 1 is equal to 0, whereas theta 4 is equal to 270. Means this is the offset slider crank mechanism which is given of case 1 type, whereas theta 1 is 0, theta 4 is equal to 270 degrees. So then after identifying what kind of offset slider, here theta 1 is equal to 0 and theta 4 is equal to 270, means it is our case 1 offset slider crank mechanism in which theta 3 formula is different. So the crank OA is rotating uniformly at 10 radians per second counterclockwise. So therefore A is equal to, here I took uniformly at, you just make a correction, it is not 10 radians per second, 15 radians per second. 15 radians per second. 15. So then small a will be 15, correct. The crank OA is rotating uniformly at 10 radians per second. This is nothing but omega 2, which is 10 radians per second in the bracket anti-clockwise, because it is a counterclockwise. Crank is rotating uniformly at 10 radians per second. If I look at the unit, it is an angular velocity, not speed. So 10 radians per second is omega 2 and it is counterclockwise, means anti-clockwise. Then length of crank OA, that is small a according to our notation, which is equal to 15 mm. If I divide with 1000, it will be 0.015 meters. Then connecting rod AB is equal to 80 mm. Hence, connecting rod length according to our symbol or notation, it is small b. Look at the diagram and tell me. So small b it is. It is 80 mm. 80 divided by 1000 is 0.08 meters. Then if I look at the diagram, I can list out two more things. One is 30 degrees. What is this 30 degree? It is theta 2. And what is this 10 mm? That is small c or small y, which is equal to 10 mm. So divided by 1000 gives 0.01 meters. Now find the velocity of the slider, that is Vc, and angular velocity of the connecting rod, that is omega 3, which is first bit. Second bit is acceleration of slider, that is A suffix c, and angular acceleration of connecting rod, that is alpha 3. So now what you have to do, you have to refer the case 1 of offset slider crank mechanism. First, the formula. First, the connecting rod formula, connecting rod angle formula, that is theta 3 is equal to, it is sine inverse of C minus A sine theta 2 divided by B. C minus A sine theta 2 whole divided by B. So now sine inverse of C, that is nothing but offset distance, which is here it is equal to 0.01 meters, minus A, that is crank radius 0.015 meters into sine theta 2, it is sine 30. So whole divided by small b, which is the connecting rod length, equal to 0.08 meters. Now if I simplify, I am going to get 1.8 degrees. Now this is to be deducted from 360 degrees in order to get the connecting rod angle, that is theta 3. So theta 3 is equal to 360 minus 1.8, which is equal to 358.2 degrees. This is the connecting rod angle. So this is case 1 for which theta 3 is this formula. Right. Remaining formulas are same. So now let us calculate the velocities. First, angular velocity of connecting rod, that is omega 3. Write down the formula. Omega 3 is equal to, by looking at the list or on your own, you try to write it so that it will be remembered forever. So omega 3 is equal to minus a omega 2 cos theta 2 by b cos theta 3. Now a value is 0.015, omega 2 is 10 radians per second, cos theta 2 is cos 30, whole divided by b is 0.08 into cos 358.2 degrees. If I simplify, I am going to get minus 1.624. It is angular velocity, therefore units are radians per second, not meters per second. If it is linear velocity or simply velocity, then you can write meters per second. Now this is angular velocity of connecting rod, therefore units are radians per second. Then further you write down omega 3 is equal to 1.624 radians per second, only figure, and in the bracket you write down as clockwise because its value is negative. According to our sign convention, clockwise is negative, anti-clockwise is positive. Next, find the velocity of slider. So that is linear velocity of the slider or simply velocity of the slider. That is Vc is equal to a omega 2 into sine of theta 3 minus theta 2 whole divided by cos theta 3. Once again, a is known, omega 2 is known, theta 2 is known, theta 3 we calculated. Substitute all the values and simplify. You are going to get the velocity of the slider as minus 0.08 meters per second. Now, therefore, velocity of the slider Vc is equal to, simply you write the value 0.08 meters per second and in the bracket you write down, because it is negative, right? So slider will move towards the crank end, right? So in the bracket I wrote it as towards the crank end. Next, find out the accelerations. In the accelerations, first angular acceleration of connecting rod, that is alpha 3. So once again here alpha 3 is equal to formula, I wrote it in the numerator. You can see the alpha 2, so that it is going to cancel because alpha 2 is equal to 0. Thereby, after cancelling that term in the numerator, alpha 3, which is the angular acceleration of connecting rod, is equal to a omega 2 square sine theta 2 plus b omega 3 square into sine theta 3 whole divided by b cos theta 3. Now substitute a as 0.015 and omega 2 is known 10 and sine theta 2 is sine 30 plus b is 0.08 and omega 3 is minus 1.624 whole square into sine theta 3 is sine 358.2 whole divided by b cos theta 3. 0.08 is the value of b and cos theta 3 is cos 358.2. With that, if I simplify, I am going to get alpha 3 is equal to 9.462 and where its units are radians per second because it is angular acceleration. In the bracket, because it is positive, we write down anti-clockwise. Then find the linear acceleration of slider, that is nothing but acceleration of slider, that is AC. Write down AC formula, from the formulas list, and first term in the numerator contains alpha 2. As here crank is rotating uniformly, hence angular acceleration will be 0. Hence the AC is equal to minus a omega 2 square into cos of theta 3 minus theta 2 minus b omega 3 square by cos theta 3. So if I substitute all the values which I know, Then if I simplify, I am going to get AC is equal to minus 1.0643, and it is acceleration, means linear acceleration. Units will be meters per second. So like that, I can solve the problems on offset slider crank mechanism. So thereby, this completes one full question on Module 3. Definitely, there is no much preparation to be carried out. You have to be thorough with, because 4-bar mechanism, again it will be little difficult. So only two mechanisms are there. So one will be given on, one question will be in Module 3 will be on slider crank mechanism. The second question in Module 3 will be on 4-bar mechanism. I have covered fully and thoroughly the derivative and theoretical part, and as well as the problems, along with some beautiful tips of remembering the formulas which are required in order to solve the problem on either inline slider crank mechanism or offset slider crank mechanism. So students, you please prepare only this much, so that definitely you can solve even in the end examination also one full question which carries 20 marks. So what are the things you have to be practice, you have to be work out, or you have to exercise in this? I am going to give a material today along with this video. I am going to post the material of PDF copy. I am going to post it. So please remember, first question, write the loop closure equation. First one for inline slider crank mechanism, second offset slider crank mechanism, third for 4-bar mechanism. This is one theory. Second theory is derive the expression for velocity and acceleration of slider crank mechanism using complex algebra method, or using the first principles, or by analytical method also you can ask. So only these are the two questions. First, loop closure equation for slider crank mechanism, offset slider crank mechanism, and 4-bar mechanism. Second, you have to be thorough with the derivative. Third, you have to be remembered along with the figures all the formulas. And then you have to, if you thorough with all these problems, whatever I solved, definitely without any doubt, you are going to solve one full question on Module 3. Okay, thank you students.